Hello again. Welcome to another review session for the final exam in Calculus 3208, presented by CDLI as always. Today we're looking at the first installment of the last unit of the course, Unit 8. It's hard to believe we've gotten this far, but here we are. So we're looking at a very important number today, one of my favorite numbers, maybe even my favorite number. It's called Euler's number. Some folks call it Euler's number, but I believe that's a mispronunciation. It's actually called Euler's number. So Euler's number is a special thing that has to do with exponentials and logarithms, and we're going to get into the details of that with this session. So here we rock and roll. All right. We're going to develop Euler's number, or see where it comes from. And one way we can get it is by looking at a special limit, so we will do that first. And then we'll talk about a natural base for an exponential function. So what happens if we use Euler's number as the base for an exponential? And then we'll compute derivatives of exponentials with base e, which is, of course, Euler's number. All right, let's roll on. So we're going to talk first of all about this special limit. So it's kind of a funny looking one. I just sort of want to describe what's happening with this special limit for a second. The limit says we want to evaluate the limit as, well, I used h here, but you can use any variable you want, but the limit as h approaches 0 of, sorry, not 0, but infinity. Wow, that's the other end of the spectrum, isn't it? So the limit as h approaches infinity of 1 plus 1 over h to the power of h. Okay, so let's think about this. As h approaches infinity, the 1 over h part of that is going to approach 0. So what we have happening here is this part is approaching 0. So inside these brackets right here, or parentheses as they're better called, everything is really going to approach a value of 1 plus 0, which is 1. But there's a competing factor here. At the same time, we're going to raise whatever we have at that particular number to the power of the same variable h. So while the stuff inside the brackets is getting smaller and closer to a value of 1, we're going to raise it to a higher and higher power to increase the overall value. So the question is, who wins? Does it go to infinity? Does it go to 0? What happens? Well, let's take a look. If we look at right here when I talk about this numerically, all I've done is I've taken a screenshot from my graphing calculator. So I asked my graphing calculator, I plugged in the formula as y equals, and I put it in as 1 plus 1 over x to the power of x, so that my graphing calculator would understand it. And I put that in as y1 in my graphing calculator. So here's the column for the values of y1 at several values of x. And so as we remember from our limits unit, when we let a variable go on to 0, we just try larger and larger and larger numbers of the value of x here and see what happens to the value of y for the formula. So it doesn't take very long at all, and we can see that we start when x equals 1 with a y value of 2, and then it does increase gradually, but you can see that it looks like these values are converging or approaching some finite number, because we get up to all the way x is going to be 100,000, and still we're trapped below 2.718 something. Well, it turns out the number is actually closer to about, looking at this limit up here, the number is actually closer to about 2.71828, etc. So that's about where we end up. So let's think about what happens when we look at a graph here. So I took the same function and I produced a graph on a piece of graphing software that I use. And what I got was this blue line, if I just start from 0, or this blue curve rather, and you can see that it levels off for bigger values of x. And we didn't even have to get really huge. I'm only out to about 16 or 20. Maybe it would be a little bit beyond that. But you can see that it looks like it's approaching a horizontal asymptote, which it is. And it turns out that that horizontal asymptote right here is a number that's just a little bit bigger than 2.5 and a little bit less than 3, and it is in fact this same number. So as x approaches infinity, we're approaching this number 2.71828. And in honor of Leonhard Euler, who discovered this, we actually shorten that because it's an irrational number. So it does, it shows a little funny pattern at the beginning, but then that goes all twisty on you. So there really is no pattern in this. It's irrational. So we call it, we give it a name, we call it E for Euler. And it's similar to numbers like pi or the square root of 2, right? Irrational, nothing really neat that's happening with them. After we go beyond so many digits, it doesn't show any particular patterns. All right. So why is that number so special? I mean, this is a pretty obscure limit, and who cares if it has a finite value? Well, let's take a look. just drew some graphs here of some exponential functions. And you'll notice for each one of these, all I did was change the bases. So you should all be familiar with exponential functions by now from your work in MA3208. So we start with 1.5 to the power of x, 2 to the power of x, 3 to the power of x, 4 to the power of x, etc. And what I want you to notice is that on all of the graphs, I've drawn two curves. The blue curve is actually f of x on every one of them, and the red curve is f prime of x, or the derivative function. And that's true of all of these curves. So what I want you to notice is that if you think about the graph of an exponential function, as x gets larger, exponentials get really big really quick. But if that's the behavior that they're going to exhibit everywhere, starting from negative infinity and going on to positive infinity, as the function is increasing, you'll notice that the slopes of the function are going to get bigger and bigger because the graph is getting steeper and steeper. So if I drew progressive tangent lines, then the slope will get larger and larger of those tangent lines, and the slopes of those tangent lines are, of course, the values that we plot for our graph of f prime of x. So all of these numbers down here on this red line are the values of the slope of the tangent of the curve, in this case for the first one, the blue curve that's above it. Now, watch what happens when I go from 1.5x to f of x equals 2 to the power of x. It's pretty much the same phenomenon, except the difference between your two functions, your blue curve and your red curve, is a lot less than it used to be. They're getting closer together. Well, let's look at what happens if I go from 2 to the power of x to 3 to the power of x. So here we are with 3 to the power of x, and those curves are pretty darn close together over here, aren't they? But one important thing you will notice, for these first two, the derivative f prime is less than f of x everywhere. For both of these graphs, f prime is less than f of x. When we go to 3 to the power of x, it's a very subtle difference, but if you look carefully, you'll see that f prime of x, the red curve, is actually slightly greater than f of x everywhere. Then let's move from 3 to the power of x to 4 to the power of x, and you'll see that f prime of x is greater still than f of x, and the gap is actually in here between the two is starting to widen a little bit. So they're getting further apart. So here's what's neat about this. Wouldn't it be cool if we could get an exponential function where its derivative actually overlapped exactly the same values as the exponential function everywhere? And if that were the case, then we'd have the function f of x and its derivative f prime being exactly the same function, which would be a pretty neat phenomenon. Well, it does happen, and if we look at this, it's going to happen somewhere between a base of 2 and a base of 3. Because somewhere between 2 and 3, if I chose a whole bunch of numbers in there to test, I could sort of play around with it until I figured something out. But somewhere between 2 and 3, I'm going to get a number for the base where f of x and f prime of x are actually going to be equal to each other. And that turns out to be at exactly e to the power of x, which we know is about 2.71828, etc., to the power of x. So when I choose this number, or exactly the irrational number e, that's when they're the same thing. And that's what's really special about Euler's number. Why is that so cool? Well, let's take a look first of all at its graph. Alrighty. So here what I've done is I've sketched a graph of, on the purple line here, get it purple where the red and the blue both overlap. Okay, so this is actually y equals e to the power of x on this graph. Now look at the data table that I've placed over here on the right-hand side. So I chose just a few standard values of x that you might use for making a table of values, okay? And you'll notice down here on the bottom, well, I've got two different y functions, but down here on the bottom it says y2 is the numerical derivative of y1. So basically this function right here, y2, is the derivative of this function right here, y1. And I plugged in y1 as y equals e to the power of x, and I just asked my graphing calculator to evaluate not only its function there, y1, but also its derivative at all the same values of x. And look at all the numbers. They're exactly the same thing. So the values of the derivative and the function itself are the same. Look, I drew one tangent line here, so let's just take this as an example. If you look at where x equals 0 on here, at x equals 0, you can see that the curve has a y-coordinate of 1 right there. That's the coordinate of the point. So y is equal to 1. let's look at the tangent line, and I asked some software to draw a really quite an accurate tangent line here. If I plot some points, every one of these is going to hit right on the corner of one of these blocks. See that? And if I calculate the slope, since this is a 1-to-1 scale on this graph, I go over 1, up 1, over 1, up 1, everywhere on that tangent line. So as it turns out, the slope of that tangent line is actually equal to 1. So the value of the derivative at that point is equal to the value of the function. Just further justification about why e is such a special number. So what have we concluded? That if y equals e to the power of x, then dy over dx is also e to the power of x. What does that mean for us? It means now we have to be able to take derivatives. Evaluate derivatives of functions when we have exponentials involved and when the base of the exponential is Euler's number, or e. Okay, so here's 4 relatively simple examples of that. So let's find dy over dx for the first one. Okay, I've got a constant multiple out here. And we should remember that a constant multiple of any function will just be a constant multiple of its derivative when I differentiate it. So this one should just be 3 times the derivative of e to the power of x, which we've already decided was e to the power of x. One great thing about Euler's number, it makes differentiation very, very easy. Aha! Now you like it, I bet. So let's take a look at this one. dy over dx in example B here. Well, I've got 2 terms to differentiate. The derivative of e to the power of x is e to the power of x. And the derivative of 3 is 0. So guess what? We're done again. See how nice Euler's number is? Okay. Now for the next one. E to the power of 3x. This is a little bit more complicated, but not terribly. If I have y equals e to the power of 3x, then I know we'll think of this as e to the power of stuff. So it's a nested function or a composite function. And when it's composite, we know we have to use the chain rule. So our derivative will be just e to the power of stuff, because that's the derivative of e to the power of stuff, multiplied by the derivative of the stuff, which is just 3. Or more concisely, we'd probably say 3e to the power of 3x. Some people get a little bit confused with that, I guess, because all of a sudden the derivative comes out of the exponent. But remember what we're actually doing here. This is just the derivative of the original function multiplied by the derivative of what's tucked inside that function. Just so happens that the place you tuck it inside is in the exponent. So that's the way it works. All right, so for the last one, dy over dx in this case is going to be equal to e to the power of x plus 3, because the derivative of e to the power of stuff is just e to the power of stuff. Then I multiply by the derivative of what's inside, and the derivative of x plus 3 is just 1. So there's not a whole lot going on there. Again, the function is its own derivative, because all we have is this little thing going on here. Nice. Okay. Let's try another example. Okay, now we're going to get down to some real difficult things. Well, not too difficult. One of them maybe, but no, we're going to have a little bit of fun here. So we're going to differentiate these functions where we're going to combine e to the power of x as a function with product, quotient, chain rule, and all that good stuff with other functions. So you knew it was coming, didn't you? Okay, so we've got a product here. E to the power of x times sine x. So this is going to be a product rule. So the derivative of the first times the second, well, that's easy. E to the power of x times sine x. Nothing to it, sure. Plus the derivative of the second. So the derivative of sine x is cosine x multiplied by e to the power of x. And that's it. We can simplify a little bit if we like, remove a common factor of e to the power of x, and then we just have sine x plus cosine x. But that's as far as we need to go. Nice. Okay. Let's take a look at part B. The first 2 are the easy ones, just letting you know. So we've got f prime of x in this case is going to be e to the power of stuff. When I differentiate it, I just get e to the power of the stuff, so 3x squared minus 2x plus 7. And I multiply by the derivative of the stuff. So that's going to be 6x minus 2. And that's it. That's all she wrote. Not really much to do to simplify. I guess you could write the 6x minus 2 in front, but I don't see that as being any simpler, really. Okay. Now we're going to have a good one here. So f prime of x. I always like derivatives with arctan because it's a cool looking derivative. Okay, so the derivative of the numerator here, e to the power of 2x, is going to be e to the power of 2x multiplied by the derivative of the inside function, which is 2x, so its derivative is just 2, multiplied by the denominator, which again is arctan, Remember, arctan is just the inverse tangent function. And then I have to subtract, because I'm using quotient rule, the derivative of arctan, which is a really cool one, 1 over 1 plus x squared, multiplied by the derivative of the numerator, e to the power of 2x, all divided by the denominator squared. So the square of arctan, well, we can just call that arctan squared x, if we like. Okay. So that one probably does require a little bit of extra simplification. So maybe a couple more steps here. We're going to have to erase it when we're all done to make room for this guy, but that should be all right. So a couple more steps here. Let's see what we can do. Let's get a common denominator for everything that's up in that numerator. So we're going to have a denominator of 1 plus x squared. So I'm going to do this relatively quickly. That's going to be 2 e to the power of 2x arctan x multiplied by 1 plus x squared to give it that denominator, and then we're going to have to add the numerator over here would really be e to the power of 2x. Woo! Get up there, x. And that's all over the new common denominator of 1 plus x squared. And rather than just flip and multiply, I'll do it all in one step here. So that 1 plus x squared is actually going to be multiplied by arctan of x, or arctan squared of x, I should say. Arctan squared x multiplied by that. Okay, so let's say one more step to simplification, because we've got a common factor of e to the power of 2x, and we just can't resist, can we? We've got to get it out of there. So let's take e to the power of 2x out of that numerator, and we have 2 times arctan x times 1 plus x squared plus, and all that's going to be left out of that bit when I take the e to the power of stuff out of there. Oh, look at me. That should be a minus sign. This was quotient rule. That's from over here. Sorry about that. All that's going to be left there is just a minus 1. Excuse me again. So that should be minus 1. And I think that's everything. Yeah, and then that's all over that really pretty denominator of arctan squared x times 1 plus x squared. Okay. Take a minute to copy that down or pause the video or something, but I've got to get rid of that now so we have room for the last one, which is, believe me, much simpler. Okay, so let's get rid of that now. It was fun while it lasted, but gotta say goodbye. See you later. Okay, so now let's try the last one. We're going to find f prime of x when we deal with this particular function now. So e to the power of stuff, its derivative will be e to the power of stuff multiplied by the derivative of the stuff there. Now when we have cosine of x squared, that's not the cosine that's squared, it's just the argument, remember that. So the derivative here is going to be minus sine of x squared multiplied by the derivative of x squared, which is 2x. Okay? So that's when we put all that business together there. So this then should give us negative, it's going to be an easier way to write that, negative 2x sine of x squared, I guess. And then better put that in brackets so we don't get confused, times e to the power of cosine of x squared. And I think that's pretty simplified for that. So there's a good answer there. All right, so taking derivatives that involve e to the power of x, super fun stuff. Here's the one more question here. We've got to find the derivative of this composite function with an arctan. So f prime is going to be, arctan is 1 over 1 plus x squared, and x in this case is stuff, squared, multiplied by the derivative of the stuff, e to the power of 2x times 2. So if I simplify, that's 2 e to the power of 2x all over 1 plus e to the power of 2x squared. I multiply the exponents to get 4x, and it looks like D is going to be the correct answer. Okay, so test question. Thank you, multiple choice. Let's take a look. Here's the your turn question. So take a few minutes to try and work it out on your own. And I'll jump to the solution slide now. So here's your solution for the your turn question. Lots of fun with exponentials. And then we have just some key ideas. So let's highlight those and we'll call it a day. So the number E is called Euler's number because it was discovered by Leonhard Euler. One way to find Euler's number is to evaluate this crazy limit as we saw. And we get a number that looks like this. If you look from the second place after the decimal. For the first 4 digits, it goes 1828, 1828. And you're like, oh great, there's a pattern, but then, nah, falls apart. Okay. As it turns out, Euler's number is the base of the exponential f of x equals e to the power of x. We call this the natural exponential because, with the exception of just horizontal translations, it's the only function that is its own derivative, which is cool. Computing derivatives involving the natural exponential function is quite convenient because it's its own derivative. Makes life easy. I really hope that helped. Hope your studying is going well. If you have any questions, put them up on D2L. Good luck. Thanks.